welcome you in the lecture series of random processes detection and estimation. It is 46th lecture of this series. In the previous lecture we have discussed Wiener filtering and Wiener predictor. In this lecture we will discuss about the Kalman filter, and the outline of this lecture are dynamical signal model and the scalar Kalman filter. In the objective of this lecture you will be able to explain what is the dynamical signal model and what is Kalman filter. Now let us start with the introduction. We have discussed the Wiener filter in previous lecture. Wiener filter is restricted to the stationary scalar signals and noise. In contrast to Wiener filter, Kalman filter has ability to accommodate vector signal and noise, which additionally may be non-stationary. It may be thought of as an sequential MMSE estimator of a signal in presence of noise, where the signal is characterized by the dynamical or state model. Now, what is dynamical signal model? Let the DC signal level in white Gaussian noise xn is equal to a plus omega n, where a is the parameter to be estimated and omega n is the white Gaussian noise with variance sigma square. The signal model A might represent the voltage output of a DC level supply, and noise omega n might be modeled as the error introduced by the voltmeter or successive measurements are taken. So Xn represents the noise corrupted observation of the power supply output. Even though power supply should generate at a constant voltage of A, but in practice the true voltage will be vary slightly at time progress. This is due to the effect of temperature component and component aging, etc. on the circuitry. So a more accurate measurement model, it would be Xn is equal to An plus omega n, where An is the true voltage at time n and small n is from 0 to n minus 1. However, with this model our estimation problem becomes more complicated, since it will need to estimate An for n0 to n minus 1 instead of just a single parameter A as in the previous case. So the MVUE estimator of An, it is A cap n, it will be Xn. The estimates will be inaccurate due to a lack of averaging, and the variability will be identical to that of noise, or you can say the variance of A cap n, it will be equal to sigma square. We can consider An to be realization of a random process to be estimated for which Bayesian approaches are appropriate. This type of modeling was discussed in the Wiener filtering. There the signal to be estimated was termed as Sn, and it was assumed to be zero mean. So by first order Gauss-Markov process, the Sn will be equal to A Sn minus 1 plus omega n, where n greater than equal to 0, and omega n is the white Gaussian noise with variance sigma omega square, and Sn minus 1 is the normal random process with mean mu s and variance sigma s square. And S minus 1 and omega n are independent. The noise omega n is termed as the driving or excitation noise. The model of equation first is known as the dynamical or state model. The current output Sn depends only on the state of the system at the previous time, or Sn minus 1, and the current input omega n. The model of equation first is also known as the dynamical or state model. The current output Sn depends only on the state of the system at the previous time, or Sn minus 1, and the current input omega n. So S0, it will be A S minus 1 plus omega 0, and S1 is equal to A S0 plus omega n, because you have Sn is equal to A Sn minus 1 plus omega n. So as1, it will be a s0 plus omega 1, or it will be equal to a square s minus 1 plus a omega 0 plus omega 1. and so on. In general, we can write as Sn is equal to a to the power n plus 1 s minus 1 plus summation k0 to n ak omega n minus k. Here Sn is the linear function of initial condition and the driving noise input from the initial time to the present time. So the expected value of Sn, Esn, will be equal to a to the power n plus 1 expected value of s minus 1, and it is equal to a to the power n plus 1 mu s. The covariance between the samples Sm and Sn, it will be CSMN. The covariance, it will be ESM minus expected value of Sm into Sn minus expected value of Sn, and it will be equal to a to the power m plus n plus 2 sigma s square plus sigma omega square into a to the power m minus n summation k0 to n a to the power 2k. Clearly Sn is not a wide sense stationary, since the mean depend on n and the covariance and the variance of Sn, it will be CSSNN. So it will be a to the power 2n plus 2 sigma s square plus omega sigma omega square summation n summation k0 to n a to the power 2k. So from here it is clear that Sn is not a wide sense stationary process, since the mean depend on n and the covariance depend on m and n here. So but as n tends to infinity, expected value of Sn, Esn is tends to 0, and covariance CSMN, it tends to sigma omega square a to the power m minus n divided by 1 minus a square, where mod a less than 1. Since the covariance becomes an autocorrelation function with RSSK is equal to CSSMN, with m minus n is equal to k, it will be equal to sigma omega square divided by 1 by a square into a to the power k, where k greater than equal to 0. And due to the Gauss-Markov process, the mean and variance can be expressed as expected value of Sn minus 1 plus expected value of omega n. So expected value of Sn, it will be a expected value of Sn minus 1, and variance of Sn, it will be expected value of whole square of Sn minus expected value of Sn, and it will be sigma square variance of Sn minus 1 plus sigma omega square, where expected value of omega n and Sn minus 1 is 0. The equation second and third are termed as mean and variance propagation equation, and with the definition of state vector, we have Sn is equal to a Sn minus 1 plus b omega n, where Sn is p is to 1 signal vector and a is p is to p noise singular matrix or the state transition matrix, and b is p is to r vector, and omega n is the r is to 1 diving noise vector. This is termed as a vector Gauss-Markov model and also known as state model. And the equivalent vector model of dynamical signal model, it is this is omega n and then b, and then we have summation of the output Sn with a z inverse, and after summing this we will get Sn minus Sn. Let us take one example. Consider two power supplies S1n is equal to A1 S1 n minus 1 plus omega 1 n. S2n is equal to A2 S2 n minus 1 plus omega 2 n, where S1 minus 1 is the normal process with mean mu s and variance sigma S1 square, and S2 minus 1 is the normal process with mean mu S2 and variance sigma S2 square. Omega 1 is the white Gaussian noise with variance sigma omega 1 square, and omega 2 is the white Gaussian noise with variance sigma omega 2 square, and all the random variables are independent of each other. Consider Sn is equal to transpose of S1 and S2n as the vector parameter to be estimated. So here you have the matrix S1n, S2n. It is S1n matrix, and it will be A1, 0, 0, A2. This is the matrix A. S1n minus 1, S2n minus 1. It is matrix Sn minus 1. Plus the matrix B is 1, 0, 0, 1. And omega n is the omega 1 n and omega 2 n. Here omega n is a vector white Gaussian noise with mean 0, and the covariance means expected value of omega m, and omega transpose n, it will be sigma omega 1 square 0, 0 sigma omega 2 square into delta m minus n. And s minus 1, it will be s1 minus 1, s2 minus 1, and it is the normal random process, and the mean will be mu s1 mu s2, and the covariance, it will be sigma s1 square 0, 0 sigma s2 square. Now the scalar Kalman filter. Since the scalar Gauss-Markov signal model is Sn is equal to a Sn minus 1 plus omega n, where n greater than equal to 0, a sequential MMSC estimator which allow to estimate Sn based on the data x0, x1 to xn as n increases. This operation is referred to as filtering. The approach computes the estimator x cap n based on the estimators for the previous time samples s cap n minus 1 is Kalman filter. It can be applied in estimation of scalar Gaussian Markov signal as well as to its vector extension. There are three different levels of generality: scalar state, scalar observation; vector state, scalar observation; vector state, vector observation. So Kalman filter is an optimal estimator. Optimal in what sense? If all noise is Gaussian, the Kalman filter minimizes the mean square error of the estimated parameters. And what if the noise is not Gaussian? Given only the mean and the standard deviation of the noise, the Kalman filter is the best linear estimator. Non-linear estimator may be better. And now the question is why Kalman filter is used. So it is used because it gives a good result in practical due to optimality and structure. And it is used because it is a convenient form of online real-time processing, and measurement equation need to be inverted. And the determination of the planet orbit parameters from limited Earth observations. Tracking targets, for example aircraft, missile using radar, robot localization and map building from range sensor and beacons. Now, so far in this lecture we have discussed dynamical signal model and scalar Kalman filter. This was 46th lecture of the lecture series of random processes detection and estimation. In the next lecture we will continue our discussion with Kalman filter. Till then, thanks for listening this lecture. Thank you.